This video lecture where we continue to talk about content contained in the book Introduction to Nonlinear Control. And in this video here, we are going to talk about input to state stability. Input to state stability is a concept of robust stability for nonlinear dynamical systems. But before we go to a nonlinear system, I quickly motivate the concept through a linear system. So here we start with x dot is equal to ax plus EW. So here we deliberately use EW instead of BU to highlight that this is a disturbance signal and not an input which we can choose. For the linear system here, we know how the solution looks like, and we can simply express it through this form. And if we additionally actually know W here, then maybe we would be able to calculate this integral here. But here we're not going to directly calculate the integral. We're going to rely on an estimate. So we take the norm of x of t, which means we also take the norm on the right-hand side, use the triangle inequality as a first estimate, use matrix vector multiplication, the corresponding norm estimate we can use here. We take the norm inside the integral, and in the end we end up with an expression here depending on e to the power at matrix, which we can take the norm of, the norm of the initial condition, and similarly here norm of the matrix E and this integral term here multiplied now with the maximal value of the function omega. And something, well, which I haven't said, but which is highlighted on this slide. So we assume in this context that the matrix A is Hurwitz. So without W being equal to 0, our origin is stable. And that ensures here that our integral here is well-defined and finite. Okay. So if we collect a couple of terms, then we can rewrite that last expression here further to obtain an estimate of this form, where we simply take these constants here, or this constant value for tau or t going to infinity, and summarize that through the parameter gamma. And if we look at this expression here, then we see that we have two separate terms. First, we have a transient bound through the parameter, the initial condition, and then this term here is going to 0 as t is going to infinity. And then we have a constant multiplied with our disturbance signal here, and well, we can do the worst case, so the largest disturbance signal here, to then obtain an estimate of this expression x. And this then can be extended to nonlinear dynamical systems, where we are essentially interested in a bound of this form. So we take a nonlinear system now, x dot is equal to f of x w. Again, w here is a disturbance, not an input. We assume that our disturbance signals are essentially bounded. Then we define input to state stability through the following property, meaning we say that a system is said to be input to state stable if there exists KL function beta and K function gamma, such that all solutions satisfy this inequality here. So this is an extension of asymptotic stability, meaning in the case of asymptotic stability, or KL stability, this second term is not present. So we have x of t bounded by a KL function, which goes to 0 when t goes to infinity. And now we have this additional term here depending on the disturbance, omega. And since gamma is a k function, that means if omega is going to 0, so the largest allowable disturbance is going to 0, then we recover our original asymptotic stability bound. But if omega is unequal to 0, well, then we have this additive term. How does this look visually? Well, we have our decay here through the KL function, but then we also have this offset, meaning our gamma of W or omega as some value here visualized through 1. We know that all solutions are bounded here by this decaying function, but then once we are in this neighborhood 0, 1, then we just know that our solution is within this window 0, 1, but we don't know if it further decreases to 0. Okay, which systems are input to state stable, and is this a sensible definition? Well, we have seen that for linear systems, in the case that the matrix A is Hurwitz, then this is already sufficient for input to state stability. So that was the first bound we have derived. For nonlinear systems, that is not sufficient, which can be shown through an example. So let's have a quick look here at this nonlinear system, bilinear system. So it's nonlinear because we are multiplying x with the disturbance signal. What we observe here, as in the first case, is that if our disturbance is not present, then we have simply x dot is equal to minus x. And then we know that this system, the origin of this system, is asymptotically stable. However, if we look at the case W equal to 2, then we end up with the system x dot is equal to x. And here we see by looking at the matrix here, so if we have x dot is equal to ax here, then the matrix is not Hurwitz, and we also see from the solution, of course, that this the origin of this system is not asymptotically stable. But more importantly, if we now look at a possible definition of this KL function and the function gamma, well, then we end up with this expression here, showing us that, this cannot be satisfied, or this inequality cannot be satisfied by a KL function and a k function gamma, since this expression here is going to infinity. This is a constant, and this should be going to 0 for t going to infinity. Meaning this is an example of a system which is not input to state stable. However, in the case that disturbances are not present, then we have global asymptotic stability of the origin. Okay, if we want to show input to state stability, as we have done in the case of asymptotic stability for nonlinear systems, then one way to do that is to define a corresponding Lyapunov function. Similarly, so this would be the case for asymptotic stability. Similarly, this is the case for input to state stability, meaning there are input to state stability Lyapunov functions which characterize the ISS property. So what we see in the definition, if we compare input to state stability with asymptotic stability, well, then we have to take this additional term here into account. If we look at corresponding ISS Lyapunov function characterizations, then we simply get this additional term here, meaning we need to be able to find a function sigma as a k-infinity function, which impacts our decrease condition, and which simply states, so if we look at this second condition here, that if we have the disturbance bounded, so then this signal here will be bounded. If x is large, or the norm of x is large, then this term here will dominate, and our Lyapunov function here needs to decrease, meaning this expression here needs to be less than 0. However, if the second term dominates in terms of sigma of omega or w being large, then this second term here can be larger than 0, meaning once we've reached a neighborhood around the origin, then we don't know how the solution evolves. Okay, let's have a look at another example how ISS Lyapunov functions can be used now to show that a system is input to state stable. And we just look at the small variation of the system considered on the previous slide. So here we look at x dot is equal to minus x cubed plus xw. So this minus x cubed term is a new term compared with the previous analysis. We have seen that without this term minus x cubed, the system is not input to state stable. So let's have a look if it is input to state stable with this additional term. And we start by assuming that there is an ISS Lyapunov function. So we define a candidate function and then want to show that it actually is an ISS Lyapunov function. And here we make the assumption that the Lyapunov function can be written as v of x is equal to 1 over 2x squared. If we then calculate the gradient of the Lyapunov function and calculate the inner product here, then we end up with this term. And there are some terms we are potentially happy with, namely if we look at these two terms here, then yes, they allow us to would allow us to define this k-infinity function just depending on x. However, this additional term here depends on x and w, meaning it is not of this form yet. So yeah, so how do we proceed in this case? And one very important tool that is used to in many proofs and then also in many steps verifying input to state stability is so-called Young's inequality. So that's what we are going to use here now to continue with our derivations here. And Young's inequality allows us to split the multiplication between two vectors in this case here. So if I have x and y and I'm looking at the product, then I know that this inequality here is satisfied where p and q satisfy this additional condition here. So if we want to apply that, we can even take another parameter into account here as well, namely by rewriting A transpose times B is equal to, now adding this additional parameter on with a multiplication in one and dividing by it in the other term, then we obtain this estimate here, separating we have started with a multiplication A times B, and now we have separated that in a sum of two terms. Okay, so we want to apply that to these terms here, where we have x squared and w, meaning in this case we are using epsilon equal to 1, p and q equal to 1 over 2, then Young's inequality leads to this estimate here. And we can simplify these two terms, which means now we end up with an expression which we were after, one term only depending on x and having the right sign and the right powers, so minus x to the power 2 and minus x to the power 4, and we have one term only depending on w, so the disturbance. Meaning we can define our function alpha and our function sigma such that we have this decrease condition here satisfied, confirming that V is an ISS Lyapunov function, meaning our system is input to state stable. Yeah, and observe here, which is, I think, a non-trivial observation, that this system here is not ISS, while the system with this additional term is ISS. Okay, so this concept allows us to characterize robust stability properties of nonlinear dynamical systems, and the way to show that a system is ISS usually is through so-called ISS Lyapunov functions. What's the context where this might be helpful? So the context where that might be helpful is in system interconnections, meaning if I have two systems, x1 dot, x2 dot, with both of them characterized through a particular function f1, f2, depending on the individual states and then individual disturbances. Now I could put them into a cascade interconnection, meaning I consider the disturbance of system 2 as the state of system 1. And now I can look at input to state stability properties of system 1, input to state stability properties of system 2, and then hopefully derive properties that guarantee that this overall system now is also input to state stable. That's discussed in detail in the book chapter. Another interconnection it might be interesting to look at is the feedback interconnection. So I have the same interconnection between the two systems here, but additionally then I'm using a controller here, depending on the state of the second system, and I could consider this as the input now of the first system. So again, what are the conditions on K now such that this overall feedback interconnection is input to state stable? Okay, you find the details in the book, it again boils down to corresponding input to Lyapunov characterizations. And that concludes the presentation for chapter 7. And in the next video, then we move on to controller designs and start with chapter 8.